Instead of using computer presentation, I would like to give a blackboard talk. I hope it's okay. So the title is Maximum Number of Complete Subgraphs. In a certain graph. And this is joint work with two other people, Dimitrios Tilikos at the Athens, and Petr Fomin in University of Oregon. But they are all doing graph algorithms, and mainly. So initially we were motivated by some other problem which were related to my own research area, but we came up with the following three problems that are related to each other. So here's the first problem. I can state it right away because this is combinatorics group, so I hope everybody is all right. So what is the maximum number of edges in an n-vertex graph? So, well, if I stop here, then the answer is quite trivial, right? So n choose 2. So then it's trivial. So let me make a modification. So, without a KR minor. So if you don't know the minor, so graph H is a minor of G if you can obtain from a subgraph of, if you can obtain H from a subgraph of G by contracting edges, right? So you have a graph H and you have G, and H is a minor of G if H can be obtained from G by deleting edges, deleting vertices, and contracting edges, right? So H is obtained from G by deleting edges or contracting edges and deleting vertices. And for this talk, I'd like to ignore all the loops and parallel edges. Okay? So every graph is simple. So now we are given some graph. Now, if I didn't have this condition, then the number of maximum number of edges was n choose 2, so it's about n squared. But if you have this additional condition, and then there are previous result. Okay, this is not my theorem. Thomason and independently Kostachka, and they proved that in such a graph, the maximum number of edges is at most certain constant times n. So it's linear, and the constant is this constant times r times square root log r times n. Right? So the maximum number of edges is at most this. And indeed, this is optimal in a sense that if you take any function which is slightly less than this as r goes to infinity, then you will have counterexamples. And Thomason even determined exact constant c. So there's, as r goes to infinity, there is a certain constant where if you take a slightly less constant, then there is a graph which violates this inequality. And if you have a slightly larger constant, no, for right constant, you can prove this. So this is somehow well-known theorem in this area. Yeah.
The constant is he determines it for, it's an exact theorem, or it's when r goes to infinity that It converges to this constant.
Right. So it's written something like 1/4 plus of 1 or something like this. So as R goes,
Yeah.
so if R is sufficiently big, then it's exactly true. But I think if R is small, then you have a better numbers. All right. So that was the first problem. Okay. And here is the second problem. And this problem, instead of counting edges, we want to count complete subgraphs. And they are normally called cliques. So a clique of graph is set of vertices which are pairwise adjacent. Okay, so it's set of pairwise adjacent vertices. Right, so empty set is clique, for instance, and a set of single vertex is a clique because they are pairwise adjacent. We all are mathematicians, so. Right. And every edge forms a clique, right? If you look at the ends of the edge, then they form a clique. So then the question is, what is the maximum number of edges in an n vertex graph? Maximum number of cliques. If I don't write the last condition, then.
But do you cliques of a certain size?
No, I don't restrict any size. So I'm asking just any cliques.
So take the complete graph?
Yeah?
Take the complete graph?
Yeah, just take a complete graph. Then it's possible that you can have 2 to the n cliques, right? So you take a graph with n vertices where every pair of them are adjacent, right? And then any subset of vertices is clique. So in such a case, the maximum number of cliques is 2 to the n. So that's not very interesting, so we restrict it. So let's assume that it doesn't have a KR minor. Right? So now the problem is different. So we are asking what is the maximum number of cliques in a graph without a KR minor. So it could be, it should be less than 2 to the n. But it could be polynomial, or it could be cubic, or quadratic, or linear. Right? But it should be at least this number, because every edge is a clique, right? So, and then any guess? Okay, why?
Cliques of size bigger than air.
Right, yeah. So for instance, you don't have a subgraph, which is, you don't have a clique of size R. So at least it's polynomial. You can have n to the r minus 1. But the nice answer is that actually it's linear. Okay, so the maximum number of cliques in such a graph is linear. Okay, so this is the answer. And originally, I had a really nice, easy inductive proof, proving that there is a certain function of R here, so that the number of cliques is at most f of R times n. And the function was like r minus 1 factorial times 2 to the r minus 1 or times some constant. But it doesn't depend on any other theorem. So you just prove it by induction. You can contract something and do induction. But later, last year, I was giving this talk. So the day before the talk, I Googled something. So I Googled this maximum number of cliques. And then there was a paper by David Wood. So this was paper written in 2006 or something. And he has a really nice lemma, and I was quite depressed because his nice lemma was even stronger than my previous bound. And so here is the idea. So look at this theorem. Then the number of edges is at most constant times r times square root log r times n. That means the average degree of such a graph is bounded, right? So because of this theorem, average degree is at most twice constant r square root log r. So that means if you have a KR minor free graphs, then you have a vertex of degree at most twice constant r square root log r. Yeah, so you must have a vertex of small degree. This is because sum of degree is equal to the twice number of edges. So let's say this number is d. And then I'm claiming that if you have a graph where every subgraph have a vertex of small degree, then the number of clicks is at most 2 to this number times n. Right? So such graphs are called D-degenerate. So graph is D-degenerate if every subgraph have a vertex of degree at most d. And I'm claiming that if graph is D-degenerate, then the number of clicks is at most 2 to the d times n. So in particular, such a graph with no KR minor, will be twice constant r square root log r degenerate. So you can prove that it's going to be, so the number of clicks is going to be at most 2 to the that number. Right? So this implies, so the number of click is at most 2 to the twice constant r square root log r times n, which is better than r factorial squared times 2 to the r something. Okay, so here is the argument. So you have a vertex of small degree. Now you count the number of clicks inside here by induction. So that's 2 to the d times n minus 1 at most. And then now I'm counting the clicks containing this vertex, which can be at most 2 to the d, because the degree is at most d. So the trivial induction, right? So he said, in his paper, he said this is a folklore lemma. So I don't know who invented it first, but this is quite depressing. So this lemma implies that the number of clicks in a KR minus free graph is at most some function of r times n. And if I have time, I will explain how we can improve this bound. So in his paper, in the last paragraph, he asked whether this can be improved. Okay? And so we don't know any right bound. So the lower bound is 2 to the r times n, which is 2 to the constant times r. So you can find the example of KR minor free graph where the number of clicks is 2 to the r times n. And I don't know any graph where you have more clicks. So, but I was able to improve this bound to 2 to the different constant r log r. Sounds better. So log r is much slower than square root log r. So okay, so that's second problem. Is everything clear? Okay, that's the second problem. Now let's talk about the third problem. Now this is a generalization of the first problem. I want to know the maximum number of edges in an n-vertex hypergraph. So instead of graph, we are talking about hypergraph. So hypergraph is what? So you can think of a graph as a pair of set of vertices and set of edges, where edges are subsets of size 2. Right? In a hypergraph, you don't restrict edges to have size 2. You can have any subset of vertices as edges. Okay? So hypergraph H is just a pair of set of vertices and edges, right? And this is a set of edges. And the condition is that each edge, E, is a subset. That's all. If it's a graph, then you need to say that each edge is a subset of size 2. Right? So this is a relaxation. Right, so now imagine that you have n vertex graphs, n vertex hypergraphs, and then what is the maximum number of edges?
What's the KR minor?
I mean, I didn't just say the last condition, so. So without that condition, then you can say, yeah, you have n vertices, any subset can be edges, where we don't allow identical edges. Yeah, it's 2 to the n, right? So if I just take those two things, then the maximum number of edges is 2 to the n. But we still want to have a similar thing. But the problem is that we don't have a minor in the hypergraph. I mean, we may have minor, but we don't have a right notion. So instead of looking at minor in the hypergraph, we will look at the minor in the instance graph of the hypergraph. Okay. So what is the instance graph of a hypergraph? So you have a hypergraph H. Then you can think about a bipartite graph, which is obtained from two parts. One side is V, the other side is E. And you have, so for each edge of hypergraph, you put vertices now. And an edge is adjacent to a vertex if this edge contains that vertex in this sense, right? So this is called instance graph of H. Let's write it I of H. And then in the instance graph, we can talk about KR minor, right? Because it's a graph. So if this instance graph doesn't have KR minor, then what is the maximum number of edges?
Each edge is a vertex of instance graph.
So the vertex.
So what is the vertex set of instance graph?
So vertex set of instance graph is V union E, right? So vertex set of instance graph is V union E, and edges are defined by this relation, right? Okay. And the answer is what? So previously we had the 2 to the n, as it. If you see the pattern here, it must be linear. So we claim that this is at most linear. So there is some function of f as the function on R, where the maximum number of edges is at most f of R times n. Okay. And I will show you how to prove P3 from P2. But before proving that, I will explain why P3 is a generalization of P1. Okay? So this is about graph. And this is about hypergraph. But still, if you ignore the function there, so there you have constant times r square root log r, but let's ignore that. Let's assume that we are only interested in the growth in terms of n, then this will imply that. That's because of the following. If the graph G, let's look at graph as a hypergraph. Then G has a KR minor. We can prove that graph has a KR minor if and only if the instance graph of the graph has a KR minor. Well, perhaps I need to assume that R is at least 3. Otherwise, it's trivial. So, why is this true? So, let me convince you by example. So, suppose that this is my graph. Okay, K3, triangle. Then what is the instance graph of this? You create vertices for each edge, right? So you add new vertices and make them adjacent to the previous ends. So what you do is just subdividing every edge exactly once, right? So that means graph G itself is a minor of this guy. You can create, by contracting these guys, you can make G as a minor, right? So that implies one direction, right? Namely, if G has a KR minor, then the instance graph will have a KR minor. And the other direction is still easy because these guys have degree 2. So if this guy has KR minor, then you can always find the you can always find the KR minor in G as well. Okay, so that implies that their instance graph will not have a KR minor, so this proves P1. Okay. And now I will explain why P2 implies P3. So we will prove that by induction. So suppose that I want to prove this is true, right? So this is at most some function f of r times n. Let's claim. And if I have an edge of the hypergraph whose one of the subset is not an edge. So this is an edge, but this is not an edge. Then what I can do is replace this bigger one by small one. Yeah? You didn't have these red edges. So now let's replace the bigger edge by a smaller edge. What you do in the instance graph is this. Previously, you had the following red edge as a set of edges. As one of the edges. And let's say this was not an edge. And by shrinking this guy into blue guy, what you do is deleting those two edges. So in the new instance graph, it doesn't have a KR minor. So by shrinking it, you still have the same property. Then by induction, you can say this, right? So it's what? It's the induction on the number of edges in the incidence graph, right? So then you win, right? So now you can assume that for every edge in the hypergraph, all subsets will be an edge. All subsets are edges of the hypergraph. So this case is easy. So we can assume that every subset of an edge is an edge. Right? We can assume that. And then there are subsets of size 2. Yeah? So from this hypergraph, look at the subset of size 2, then you just take a subhypergraph, but which is graph, right? And whenever you have an edge in the hypergraph, then every pair of them, there is another edge, which joins only 2 of them, right? So you go to this situation. So you have a graph where every edge of the hypergraph induces a click. Right? So you can apply this. So the number of clicks in a graph will be an upper bound. So you can use the same function. Right? So that proves that P1 somehow gives you some answer for P2, and P2 gives you some answer for P3, and P3 gives you some answer for P1. Now we can also talk about planar graphs. So what happens if it's planar? Well, planar graphs doesn't have K5 minor, but by Euler's formula we know that the number of edges is at most something, right? So Euler's formula implies that the number of edges is at most 3n minus 6. And then this implies that every planar graphs have a vertex of degree at most 5. And so it's 5 degenerate. So it's going to be 32. So the number of clicks is going to be 32n or less. Right? But David Wood proved that in fact the right answer is 8n plus something, which I don't remember. So this is his paper. So this is improvement over 32, right? So if you get a silly bound, you get 32, but now he can improve it to 8n. And he determined what graph can have a maximum number of clicks. What about P3? For P3, we are interested in the number of edges in a planar hypergraph. So we call a hypergraph is planar if its instance graph is planar. So if we apply same bound, then this A then should give us same number, right? So at least we know that the maximum number of edges in the planar hypergraph is at most 8 times n plus something. Why is it 8? Oh, okay, 8 times n. So if it's planar, then David Wood's bound would give us 8 times n. But in fact, we can prove that it's 6 times n plus something. So
this last one is the instance graph. Oh, I don't understand.
Yeah, so
Maximum number of edges in the hypergraph.
whose instance graph is planar. But if you look at the references, people call planar hypergraphs when their instance graphs are planar. So in such case, you draw edges as a face, some reason, but that's same as putting a vertex and making edges. So both definitions make sense. So before proving this thing, I will show you how to prove this planar case result. So I showed this proof to Richard Stanley when he visited last year, and he said, "Oh, this is new to him." So the proof is easy. So this uses only Euler's formula. So Euler's formula is the most important thing for planar graphs. So we'll count number of edges based on the number of vertices inside edges. Right? So they are called RET. So based on number of vertices in an edge. So how many edges have 0 vertices? Yeah. So empty set can be an edge. So there is only one possible edge which has 0 vertices in it. How many edges can have one vertex? N, right? How many edges can have 2 vertices? Well, that's the same as this, right? So look at, so each edge looks like a subdivision of planar graph. Am I saying? So what will be the maximum number of edges where you have 2 vertices? That's going to be same as number of so if every edge has exactly 2 vertices in it, then the graph is instance graph of a planar graph, right? And then the number of such edges will correspond to number of edges in a planar graph with n vertices. So it's 3n minus 6. Okay. Use same theorem by Euler's formula. So what's remaining is number of edges where each edge contains at least 3 vertices. Alright, now here's a construction. So you have n vertices. I will draw them as red colors, and you have a number of edges. And I'm looking at instance graph, right? So what we can do is to draw a cycle going through vertices. Okay, so for each edge, so for each yellow vertex, you draw a cycle going through vertices. And so you draw cycle, and then remove the yellow guys. Okay, so you remove the yellow guys. So what is this? Yeah, this is planar graph with n vertices, and then number of edges is at most number of faces in this planar graph. Okay, each face can contain at most one edge vertex of the instance graph. So that's at most the number of faces in a planar graph. And if you know this, you can somehow assume that it's connected. Number of edges is 3n, let's say n. If number of edges is 3n minus 6, then it's going to be 2n minus 4. Right? So number of faces at most it's going to be at most 2n minus 4. Okay? So you sum up these numbers, what you can get is 6 times n minus 9. Right? So this is a way to prove that every planar hypergraph have at most 6n minus 9 edges. Right? Any questions?
2n minus 4, isn't that the maximum number of edges of a bipartite planar graph? This number 2n minus 4, isn't that the maximum number of edges in a bipartite planar graph?
Oh, that is it? Oh, then it's
You double count, right? And cycles cannot have
Yeah.
three, so
right. That makes sense.
is there a connection there since you're looking at
Yeah, because you can. But I'm not sure. If you have a vertex of degree 2, you have to do some other trick. But if you assume that every vertex in the one part has degree at least 3, then what you're saying is correct. So maybe if you have a smaller degree vertex, you can just reduce it by induction. So yeah, basically the trick should be same. But it could be that this is.
maybe it's coincidental.
Yeah, there could be similar work. Yeah, thanks for pointing out. Alright, so let me prove another easy proof for this, which wasn't known to me. And so we were trying to prove that the number of clicks is at most 2 to the constant r log r times number of vertices. So let me begin with Thomasson and Kostachka's result. So number of edges is we know that number of edges is at most constant times r square root log r times n. Yeah, that's by Thomasson and Kostachka's result. And then what is the number of triangles? Yes, the clicks of size 3. Well, you can count. Look at this graph. The number of triangles in such a graph. So let's look at the number of triangles containing this vertex. Yeah, that will be the number of edges in this area, right? For each edge, you have a triangle, right? So that means it's so for each vertex, let's count. For each vertex, you count number of edges in the neighborhood. So the number of edges can be given by this formula, but this neighborhood doesn't have a KR minus 1 minor instead of KR. Yeah? If this guy has KR minus 1 minor, so this guy has no KR minus 1 minor. So the number of edges inside this neighborhood is at most constant r minus 1 square root log r minus 1. That's this coefficient times the degree of the vertex. Right? So degree of V, right? That's the size of this neighborhood. And then each triangle is counted 3 times. So divided by 3. Alright. And then what is the sum of degree? That's twice the number of edges. So this is, and twice the number of edges is this. Right? So 2/3 constant squared r minus 1 square root log r minus 1, but let's just take a square to be simple. Yeah, I mean that's anyway it's upper bound, so r is bigger than r minus 1, and then number of vertices. Right. So the number of triangles is 2/3 times c to the c squared r minus 1. This. And you can repeat this, right? You can repeat the same procedures. Number of clicks of size 4, the same, except you plug in this formula here and divide by 4. So what you can get should be 4 times 3 constant cubed, and I'm guessing without something like this. Right? So you repeat this until you get clicks of size r minus 1. And then something should be familiar. This part looks like you have r choose 2 something. No, right. So r choose 2, r choose 3, r choose 4, r choose 5. So you have a binomial sum. Right? So I will be just rough, but roughly speaking, when you sum up, you get something like 1 plus constant r square root log r. No, this r, yeah, to the r, something like this. If you calculate enough. So what is this? This is about e to the r log of 1 plus constant square root log r. Oh yeah, I have n here. And oh yeah, let's replace it by 2. And this, let's ignore this 1. Yeah, so that's 2 to the r log square root log r times n with a certain constant. So this is what? This is log of square root of log r is log r, right? So you can get the desired result. So not bad, not bad. So this is the best upper bound that I can get. So the best lower bound I have is still 2 to the constant r n. So it'll be interesting to close this gap, right? Either improve this upper bound, yeah, either improve this upper bound, or increase the lower bound. Find some graph or randomly or some nice graph. So one.
What is the construction? What is the construction?
It's trivial construction. You just consider kr minus 1. They have clicks of size, and they have 2 to the r minus 1 clicks. And you glue them. Yeah, quite trivial, right? But there are slightly better constructions. But anyway, you have a clicks of size kr minus 1. You glue them with a cut set of size r minus 2 or something. Then you don't have a kr minor. You glue them you glue clicks of size r minus 1 many times. You will have a large number of clicks. Should be something like this. So this is far from being random or something. But Thomason's and Kostachka's result actually uses random graphs. So in order to get a right bound, perhaps you need the random graphs to construct this kind of parameters. Or maybe this is true. Maybe this is indeed real truth, but I don't know. So that's all I have. Okay. Thank you. Thank you for listening.
Any questions or comments? He's very hungry. If not, let's thank the speaker then.
Thank you.